So let us try to see di class of non-randomized invariant estimators. So let's see what is the definition of a non-randomized invariant estimator. So it says the two actions should correspond and the two decision rules should also be same. So what is the observation in the second case, second problem? In fact, delta of GCX. So delta is invariant if and only if delta of GC of x1, x2, xn. So this is when the units of x1, x2, xn has been changed, or this is the case when I observe x1, x2, xn. So these are situation of the second problem. It says, since your problem is invariant, you can get the decision of the second problem by just changing the decision in the first problem appropriately. So corresponding to GC, I know the xn equivalent xn is GC tilde. So this is same as GC tilde of delta of x1, x2, xn. Right. So these are transformed xn. These are transformed observation. So what does, and you use the same delta. So this is due to principle of invariance. This is says equivalent saying that delta of x1 plus c, xn plus c should be same as gc tilde of delta x1, x2, xn, but gc tilde a is nothing but a plus c. So I write down this as delta of x1, x2, xn plus c. This should happen for every c belonging to R. So if I want, I can put c is equal to minus xn. This becomes delta of x1 minus xn, and there will be xn minus 1 plus c. So xn minus 1 minus xn, and xn c I have taken as minus xn. So this becomes 0. This is same as delta of x1, x2, xn. C I have taken as minus xn. So what does this say? So I get immediately the form of any invariant estimator. So delta belongs to di if and only if delta of x1, x2, xn is nothing but, I can take this over here. So xn plus this quantity. So this is only a function of x1 minus xn and xn minus 1 minus xn. So I can write down that as minus of u of x1 minus xn, xn minus 1 minus xn. I can call them as d1, d2, dn minus 1. So what does this suggest? Delta is invariant under the given group of transformations if and only if my delta is of the type xn minus u times d1, d2, dn minus 1 for some u which is from Rn minus 1 to R, because u is a function of d1, d2, dn minus 1. So it is defined on n minus 1 Euclidean space. So any invariant decision rule is of this type. So it would be xn minus some function of x1 minus xn, x2 minus xn, and xn minus 1 minus xn. Now note that if I just consider delta not xn as xn itself, not delta not xn, I consider delta star of x1, x2, xn as xn ln. Is this invariant? So let us look at delta star of x1 plus c, xn plus c. This is nothing but last component, xn plus c, which is nothing but xn was same as delta star of x1, x2, xn. So what does that mean? Just xn alone as an estimator is invariant under G. This happens for every C. So to have a much more flexibility, I want to see if I can replace here xn by any invariant estimator, because xn is invariant. The question arises, can I say that delta is invariant if and only if delta is same as some invariant estimator, any given invariant estimator, minus some function of d1, d2, dn minus 1? And the answer is yes. So let me do that in the form of theorem, which is straightforward, but we can just have a quick proof of that. So let's try to see that. So theorem. Delta belongs to di. So let delta naught belonging to di be fixed. So what it says is delta naught is a given invariant estimator to us. Then it says that delta, any other invariant estimator, that means if delta is an invariant estimator, it has to be of the type delta naught x is equal to, sorry, delta x is nothing but delta naught x minus u of d1, d2, dn minus 1 for some So this delta naught you can choose as per your convenience. So you choose any delta naught which is invariant, then you can say that any other invariant estimator would be of the type delta naught minus u of d1, d2, dn minus 1. And the proof is straightforward. So you can call this as star. So suppose delta is of type, is of star type. That means delta is same as invariant estimator delta naught minus some function of d1, d2, dn minus 1. What I have to show is delta is invariant. Delta is invariant means delta of x1 plus c, xn plus c is same as delta of x1, x2, xn plus c. So see that for any c belonging to R, delta of x1 plus c, xn plus c. By definition, it would be nothing but delta naught of x1 plus c, xn plus c, minus u of d1, d2, dn minus 1. d1 is nothing but x1 minus xn. So it would be nothing but x1 plus c minus xn plus c. And dn minus 1 is nothing but xn minus 1 plus c minus xn plus c. Because what is happening over here? My observations are x1 plus c, x2c plus c plus xn plus c. So it is same as delta naught of same x, x1 plus c, x2c plus xn plus c, u of x1 minus the last component, x2 minus last component, and so on. So this minus last component is nothing but x1 minus xn, and that is what I'll get over here, because this c will get cancelled, this c would get cancelled. So this is nothing but my delta naught is invariant. So delta naught of x1 plus c, xn plus c is same as delta naught of x1, x2, xn plus c. Why? Because delta naught is given to be invariant to us, because I have chosen delta naught to be invariant, minus u of x1 minus xn, xn minus 1 minus xn. But these two quantities together are nothing but delta x. So this is same as delta of x plus c, which means that delta is in or delta is invariant. Now, conversely, delta is invariant. So, I have to show that delta is of this type for some function u. So, I have to guess what u would be. In fact, I can guess my, so let u of u star of x1, x2, xn is nothing but delta naught of x1, x2, xn minus delta of x1, x2, xn. Note that delta naught is given to us. Now, this delta is also given to you. So, delta and delta naught is given to us. Constructing u is not difficult. So, I construct u star x1, x2, xn is delta naught of x1, x2, xn minus delta of x1, x2, xn, because that is what this u should be. The only thing I have to show that this u star depends on x1, x2, xn only through x1 minus xn, x2 minus xn, and xn minus 1 minus xn, because I have to show that whatever that u is, that is a function of d1, d2, dn minus 1. So, this is same as, so what I see is u star of x1 plus c, xn plus c is nothing but delta naught of x1 plus c, xn plus c minus delta of x1 plus c, xn plus c. But delta naught is invariant, that is given to us by the hypothesis, and delta by choice is a invariant. So, both are invariant, so this would satisfy delta naught of x1, x2, xn plus c minus this would satisfy delta of x1, x2, xn plus c. So, this c gets cancelled, you get delta naught of x1, x2, xn minus delta of x1, x2, xn, which is same as this, which is nothing but u star of x1, x2, xn. This happens for every c belonging to R. So, what you get is u star x1 plus c, xn plus c, same as u star of x1, x2, xn. So, you can choose c to be minus of xn. So, what does that give you? Because this happens for every c belonging to R, so I can choose c to be minus xn, so it gives u star of x1 minus xn, xn minus 1 minus xn. 0 is same as u star of x1, x2, xn. So, what does that mean? That means my delta naught x or delta of x1, x2, xn is same as delta naught of x1, x2, xn minus u star of x1, x2, xn which is same as delta naught of x1, x2, xn minus u star of x1, x2, xn is nothing but u star of so which implies that now this is only a function of d1 which is x1 minus xn and dn minus 1 which is nothing but xn minus 1 minus xn. So, this same as I can call this whole function as only function of d1, d2, dn minus 1, and I can denote that function of d1 by d1, d2, dn minus 1. So, I have got the form of any invariant decision rule. So, let me write down how does an invariant decision rule looks like? So let delta naught belonging to di be specified. This is as per our choice. You can choose any invariant estimator delta naught. Then di is nothing but collection of all those delta such that delta of x1, x2, xn is nothing but delta naught of x1, x2, xn minus u of d1, d2, dn minus 1 for some u belonging to Rn minus 1 to R. So, I have defined the class of all invariant rules. Let us see how the risk of an invariant decision rule would behave. Now, we have done a result that if my G bar acts transitively on the parametric space, then the risk is not going to depend on theta. So, first let us try to see what is the risk of an estimator for delta belonging to di R. So, let me call this as u because it depends on what u you have chosen. So, R delta u theta, which is expected value of w of delta u x minus theta. These all are non-randomized estimators, so there is no second stage of randomization. Yeah, so this is same as expected value of w of delta naught x1, x2, xn minus u of d1, d2, dn minus 1 minus theta. Theta belongs to capital theta. Now, note that if this risk function didn't depend on theta, then my life is further simplified, because then I know that risk of any invariant estimator is constant. And then finding a best estimator may not be that difficult. So, let us try to see whether G bar acts transitively or on theta or not. To show that G bar acts transitively on theta, what I have to show? So that if I take 2 points theta 1 and theta 2, they are related through G bar C for some C. So, let theta 1 and theta 2 belongs to theta, which is same as real line. I can write down this as theta 1 as theta 2 plus theta 1 minus theta 2. So, this is theta 2 plus some constant. So, this is same as g of theta 1 minus theta 2. Theta 1 is in R, theta 2 is in R, so theta 1 minus theta 2 is in R. So, what it says? So, for any theta 1 and theta 2 belonging to R, there exists a C, which basically I know what that C is, theta 1 minus theta 2 belonging to R, such that theta 1 is same as GC of theta 2. That means any 2 points, sorry, G bar C of theta 2. These are G bar C. That means any 2 points in the parametric space are related through G bar C, and which is equivalent to saying that G bar acts transitively Once you know that G bar acts transitively on theta, what does that mean? That means risk of any invariant estimator is constant. So, this implies that for any invariant estimator delta belonging to di, R delta theta is constant. it does not depend on theta, or in other words, it is same for every theta. So that means r delta theta is same as r delta 0 for every theta belonging to theta. So risk of any invariant estimator is constant. So what I do is, so the question is, does there exist an invariant decision rule delta star in DI such that R delta star 0 is same as infimum over delta belonging to DI of R delta 0, because risk of any invariant estimator at theta would be same as R delta 0. So I don't have to minimize it for every theta, because it does not depend on theta. So if you minimize it only at one point, theta is equal to 0, you're done. So this is what the goal is. So the whole problem has simplified only to this fact. So you have to find an estimator which minimizes the risk at theta is equal to 0 among all invariant estimators. So in the next lecture, we'll see how to go about it. And then we'll see that in most situations, under wherever you have a location invariance, the best invariant estimator exists. So that's all for today. And next lecture, we'll try to address this problem. Thank you very much.